My talk is about computing with hypervectors, and sort of as an introduction, I mean, you want to know what hypervectors are, what I mean by hypervectors. They are high dimensional, something like 10,000 dimensional, and the important thing that they are this large number, like 10,000, and they can be bits. These vectors can be vectors of integers, or they can be of reals, or they can be complex numbers. The dimensionality is the important thing. The nature of the dimensions, there's a lot of choice in there. These vectors are either random or pseudo-random, and the vector components, they are independent and identically distributed. This independence can be guaranteed only at the start when you start building a system. Based on these ideas, they no longer are necessarily the various vectors you produce, not necessarily independent, but they are still identically distributed when you use the operations that I will talk about. And the important thing is that it's possible to build a fully general system of computing based on hypervectors. And this computing is transparent and has many positive qualities we associate with the brain. And by transparent, I mean that you can actually understand what went into the result. You can analyze it, break it into its components as if you were factoring. And this kind of computing is robust and noise tolerant, and that's part of the things that comes from high dimensionality. It can learn fast. We can demonstrate one-shot learning, and when we talk with psychologists, it turns out that one really is something like 5. So one-shot learning means that you do not have to repeat very many times before you can produce a permanent memory or learn something permanently, or relatively speaking permanently. Can integrate signals from disparate senses, so it should be good for multimodal information handling, and it allows simple algorithms at scale to large problems very efficiently, and it allows high degree of parallelism. And here is an example, learning by analogy. Here's an example. What is $1 in Mexico? We understand it immediately. I don't think anybody really has a problem with that question, but that is sort of a perennial problem with traditional AI and also traditional neural nets. But it can be solved with hypervector mapping or multiplication, and I will return to that before the end of the talk. And this talk is about the mathematical theory of hypervector computing. The theory dates back to 1990s and goes by names of holographic reduced representation, or binary spatter code, or vector symbolic architecture, although semantic pointer architecture is in the very same family of things. The underlying math itself is late 1800s, early 1900s, and it's referred to as abstract algebra, modern algebra. So modern here is 100 years old. But the math itself is somewhat subtle, but it's much simpler than the name abstract algebra might suggest. So when I talk of abstract algebra, you don't have to worry that we are getting or to use these ideas that you have to somehow get into some very esoteric concept. You're still working with concepts you already learned probably in elementary school or in high school. And this theory of computing can be made by nanotechnology. It requires very large circuits, and this is what nanotechnology promises to deliver for us. It tolerates variation in the components, and the architecture allows a very high degree of parallelism, which reduces the need for fast switching and hence improves energy efficiency. And computing with hypervectors, it complements traditional numeric and symbolic computing and traditional neural nets, including deep learning. Computing with hypervectors, it actually resembles ordinary computing with Booleans and numbers. That's what we all know and have grown up with and think of as computing now. And it includes a memory for the high-dimensional vectors. And it has to be high-capacity memory so that you will not lose what you have learned one day and you wouldn't be able to recall a week later because you learned something new in between. So the high capacity is essential, and it has to be content addressable. The operations on these vectors, they resemble addition and multiplication. And now we have to use a little bit of terminology for algebra. These operations form an algebraic system that is actually richer than a field. So you may not be familiar with fields as such, but you have dealt with them anytime you have computed with ordinary numbers. The number arithmetic is based on the algebra of fields. And now we have a system that's actually richer than a field. So we might expect to get something interesting, new things coming from it. And a caution, the algebra of hypervectors, it's not identical, or it's not a subset of linear algebra. I mean, linear algebra is fine, but this kind of computing with hypervectors has additional elements. And here I'm going through an example of the kinds of operations you would have on these high-dimensional vectors. First of all, they are the things that you start with. I call them seed vectors. And here I demonstrate them with vectors of plus ones and minus ones. So think of a seed vector A. It's just 10,000 randomly placed ones and minus ones. And such a seed vector could represent a letter of the alphabet, for example. It could represent a word in the vocabulary. And how do you operate? I've mentioned addition operator. Actually, addition of these vectors would be just ordinary vector addition. So it goes coordinate by coordinate. Multiplication is also coordinate by multiplication. You just take in each coordinate and multiply, and so if you have two ones, the product for that position is 1, and 1 and minus 1 produces minus 1. If you think of this sort of as on binary vectors, multiplication is the exclusive OR operator. It's equivalent to what we have here in this slide. And it's to be noted that if you multiply a vector by itself, you get all ones, and so it means that the vectors in this particular system, they are self-inverses. And there's an added operator, the one that is added to the field that we deal when we deal with numbers. It's a permutation, and a simple rotation of coordinates works very well as the permutation operator. And now you have to be able to compare these vectors that you produce in this system, and the cosine is a very good measure for similarity of vectors. The cosine of a vector itself is 1, so it is fully similar. With the complement of the vectors -1, and if the cosine is 0, exactly 0, the two vectors are orthogonal. And here's what I say is one of the important things that we get with high dimensionality, is that if you randomly take two vectors, they are approximately orthogonal. And I refer to this as the blessing of dimensionality, to contrast with what people call the curse of dimensionality. Actually, high dimensionality is what gives us many of the desirable properties of computing with these hypervectors. And now this is a little bit technical slide, so just bear with me. Some key features of the algebra, and I've marked here some that are familiar to us from just number arithmetic and others that are added when we go to the vectors. Now, addition is commutative. It means that you can change the order of the vectors that you add and you get the same result, same as with numbers. Addition, multiplication, and permutation are invertible. Well, that's true in addition and multiplication of numbers. With numbers, you don't have the permutation operator, so that's why you get the asterisk in that line. Multiplication distributes over addition. Again, familiar from computing with numbers. Now here, this new operation, permutation, distributes over both addition and multiplication. And so that gives you new power to build computing on. Then also the output of addition is similar to the inputs, whereas the output of multiplication and permutation outputs are dissimilar to the inputs. And that, again, will play an important role in what we can do with these vectors. And there's another one, multiplication and permutation, they preserve similarity. And so, as an example of how such vectors and operations would be used, I will go through how you encode with these things. I mean, this next section in this talk, it sort of it relates to when you first encounter programming. I mean, it's a strange world. You have to have variables and you have to have instruction and all those things. This is the equivalent. What I'm doing in this next couple of slides is the equivalent of when you first face programming and have to learn this new esoteric world where you represent, how do I represent the sequence? How do I represent the set? How do I say that a variable has certain value? All this thing. By now, I think about every one of us just has absorbed that and doesn't even think about it. So here I'm just showing how the very, very basic operations now can be done with hypervectors. If you want to encode a pair, like x having the value of a, you use some sort of binding operator, and the binding can be done with the multiplication operator. So here, the line which sets p equals the x multiplied by a, it just represents the idea that x is associated with a. It could be the association could mean something like the value of the variable x is a. And when we have a bound pair, then you can extract one of the arguments if you know the other. And here we use again the multiplication operator to extract the other element of the pair. And the lines reads x times p, and then that is, okay, the p has been expanded into x times a, and now the 2x is, I think this is associativity. You can put them next to each other, and then they cancel each other because, as I previously already said, that these vectors are self-inverses. So in the end, when you do this multiplication, you find when you have the pair and you have one of the elements, you can find the value or the vector that represents the other element. Now we have to encode sets in some way, and it turns out the addition operator is just ideal for encoding sets because addition is commutative. So in a concept of set means that it doesn't matter in which order you put the elements. So addition is a very good way of encoding sets. Now you have to encode data records. That means something like x equals a and y equals b and z equals c. Now that can be encoded with a sum of bound pairs. And so that's the line d equals x times a and so forth encodes a data record. And if you want to extract the value of one of those variables from the record, you multiply with the vector that represents the variable. So that's the line x times d equals, and then there's a lot of math. And the last two lines are the interesting ones. It ends up that all those operations, actually very, very simple. Things cancel out so that you get A plus what I mark as noise, and it turns out that the vectors that are not equal to A, they are different from anything else that a system has encountered so far. So we just can call them noise. And it turns out in high-dimensional space, you can tolerate a fair amount of noise and still identify that, yes, this noisy version of A is the result. Noisy result actually should be the A. Now, encoding sequence is there. Order does matter. And here, a simple way of encoding the sequence B followed by A is that you will rotate the first vector and then you multiply it with the second. So it's rotate on A times B, and if you want to extend that with C, then we rotate what we have so far and then multiply that with C, and when you break that out, you get something like 2 rotates of A times 1 rotate of B times C by itself. And then from this 10,000 dimensional vector, we can extract any one of the elements by using, again, the very same operations, including the inverse operation of the rotate. So that last little bit of arithmetic, it says that there are parts that cancel out each other. The R rotate of B and C, they cancel out each other, and then the counter-rotating a twice rotated A then recovers A. These representations, and when you use these operations, these representations produce vectors that are holographic. That means that every piece of information that is encoded into the vector is distributed over every one of the vector coordinates. That means that every subset of the vector is computing the same thing. So there's no coordinate that is critical. And this is what gives us robustness. And a set of these operations I have described to you in a couple of slides, in the previous slides. It's complete in a sense that you could actually implement a neural hypervector Lisp. And so if Lisp is a complete system of computing, you can provide a complete set of computing with these operations. Now I'll go through 3 examples where we have used these ideas to actually produce something that is interesting and actually can be developed into useful algorithms. And the first one deals with language vectors. We made 10,000 dimensional language vectors for 21 European Union languages using seed vectors for letters as the starting point. And then with these seed vectors and the sample text, we produced language vectors encoding either the trigrams or the tetragrams of the language of any individual language sample, and the encoding of the n-grams used the operations of the rotation and multiplication, and then all the n-grams were then summed into a single language vector. And then when we studied these language vectors, they cluster according to known language families. So there, the Romance language is upright, and and there are Baltic languages toward the bottom and Slavic languages to the left. So it's very simple algorithm produced vectors that were very nicely sensitive to, the letter structure. In some sense, it reflects the sound structure of a language. So it was sensitive to how words or languages look or sound. And I think this kind of algorithm could also be used for finding out what the file type is. There was, I think it was a previous talk here. Then we tested these language vectors, whether they can be used to identify samples from these same languages, and we had 21,000 test sentences, 1,000 sentences from each of the languages, and then we compared the language vector computed for a test sentence to the language vectors that we had computed from known text samples, and we got about 97.8% accuracy, which is, for the simplicity algorithm, actually, we were very surprised, because this was done as a student project, and we continuing on this work now also as a student project at Berkeley. Another example, semantic vectors computed random indexing. Now, semantic vectors have been around for at least 20 years, and probably the best known method of computing semantic vectors is latent semantic analysis. What it means is that you will go through a lot of text, and for each word in the vocabulary, you produce a high-dimensional vector, and then you compare meanings of words by comparing the vectors. And when this kind of semantic vector calculation done with latent semantic analysis, then the random indexing of the same data set produced equivalent scores on test of English as a foreign language. Now, the difference in these two things is that singular value, latent semantic analysis requires singular value decomposition, and its complexity is sort of grows with the square of the number of documents. And random indexing is linear in the square. So in our experiment, we went through 37,000 documents in 10 minutes using random indexing, and it took over 2 hours with latent semantic analysis. And if you extend this to something like 1 million documents, then 10 hours for random indexing would be versus 300 days for latent semantic analysis. This sort of gives an idea of how some of these different algorithms scale and what it means in practice. This random indexing algorithm, it's a form of random projections, and there's a company in Sweden that has scanned news articles in several languages. It's random indexing since 2008. So it's actually being used commercially in the sense that the company mainly does just that as their way of doing business. And then my third example is an analogical mapping with multiplication by a hypervector. And we come back to this question, what's the dollar of Mexico? Which will be handled by encoding United States and Mexico in some form, and in this case, we represent each of these countries by what's the country's name and what's its capital city and what is monetary unit. And so for USA, the vector representing the United States, the name is US, capital DC, and monetary unit is dollar. So each of those things on that line, USA is a 10,000 dimensional vector, NAM is a 10,000 dimensional random vector, US is a 10,000 dimensional random vector, CAP 10,000 likewise. And so USA becomes the sum of products of vectors. Likewise Mexico. And if you pair the two, in some sense you have to bind them, you multiply those two together. And if you analyze that pair, go through just a little bit of arithmetic, it turns out that pair that has been gotten with multiplication, it includes as its elements US, it includes as the corresponding US and Mexico, the names as a pair. It includes the capital cities as another pair. It includes a dollar and peso as another pair, plus noise. And this noise, again, it comes from things where things don't cancel out. Now, if we take a literal interpretation of dollar Mexico, that would be handled by you multiply the vector for Mexico with the dollar, with the vector for dollar. And when you work it out, as I've shown here, you end up with three product terms. The first one is dollar times the name times Mexico, and the other is dollar times the capital times Mexico City, and the third is dollar times money times peso. And it turns out that all of those are random relative to what the system has ever been taught. So nothing cancels out, and so in some sense, there is no such thing as the dollar in Mexico. But however, if you take the vector that represents the correspondences, and this is the vector we call pair. The pair was gotten by multiplying the vector for USA and the vector for MEX, multiplying them together. If you take that pair, then when that is worked out, you actually get three sources of noise, but there's one cancellation, and that's the dollar cancels dollar, and you're left with peso. And so as a result, we have a vector that is composed of peso plus some noise. And that is close enough to peso to be recognized as the correct answer. So what I've shown is that these operations actually can be used in interesting ways that resemble what we do in ordinary programming, and also something that is not available, and that is the multiplication operators that worked as a mapping. And so as my parting thought, I'd say the cognitive and computational powers of the brain are intimately related to the mathematical properties of high-dimensional spaces. And I mean truly high, I mean 10,000, 100,000. I would say 600 in this game is not high. And that really has to do with the number of nearly orthogonal vectors that you get. It also has to do with the law of large numbers, where when you have in the law of large numbers that averages, relatively speaking, they are very stable. And these kinds of spaces can be understood in terms of their geometry and algebra. And a mode of computing that exploits these properties is made practical by nanotechnology. And so I want to thank my collaborators, Aditya, Johan, Andrew, and these are either undergraduates or graduate students or professors here. And also we had funding from DARPA through the SONIC project and Intel. So, and I thank you for your attention.
Other questions?
Yeah. Winfried Wilger, IBM. This reminds me very much of sparse distributed representations, which seem to play an important role in the brain. In sparse distributed representations are also very high-dimensional vectors.
I have a hard time hearing. There's some echo here.
Oh, that's my accent.
Yeah.
It is believed that sparse distributed representations, which are very similar to these hypervectors, play an important role in the brain. These are also high-dimensional vectors, but most of the bits are 0 and only a small number are ones. How does the mathematics of this relate to that?
There are a lot of, this is really what I've talked about, is just sort of some basic ideas. Sparsity definitely is an important thing to be included and studied. But you still want to get a system that has these operations, but they just work on sparse vectors.
Yeah.
Yes, no, absolutely, and I'm sure. Also, same thing about spikes. You know, they are both sparsity and spikes are energy efficient ways of implementing computing.
Okay.
So I fully agree.
Okay, thank you.
Yeah.
So in several of the examples that you gave, there was a noise vector.
Yeah.
It wasn't clear to me how the noise vector was distinguished from the signal vector, or how you made that separation.
Okay, for this kind of thing to work, you have to have a bookkeeping section where you keep track of every vector that the system knows about. And that is would be the function of the associative memory. And if you approach the associative memory with something that is not stored, it tells you that. If you approach it with something that is similar to what was stored, it'll find the answer. So the associative memory is an essential part of an architecture like this.
2 more quick questions.
That was a fascinating talk. My question is actually a bit related to the previous one. And I'm just wondering if you've thoroughly analyzed the way that the noise scales with the number of components of pieces of information you're encoding.
Yeah, it sort of comes to close to the idea of magical number 7 plus or minus 2. In the sense that if you add many things together into a sum, you cannot resolve the sum into its components. However, you can add many things into a sum and ask, is this one of the components in the sum? There you can find a very, very much larger number that you can tell, okay, yes, no, I have a sum of 1,000 vectors. And then you come with one vector that is in the sum. Is this part of it? And you said definite answer, yes. If you come with a vector that is not in there, you come with a very definite answer, no. So,
thank you.
Yeah.
You just answered my question, so thank you.
Yeah. I made some printouts of the dollar of Mexico because it's a little bit involved, and so people who are interested can just pick.